Okay, our third speaker is Ruihui, and he will give a talk on 3D geometry learning from unsampling to generation. So Ruihui is currently a postdoctoral fellow at the Chinese University of Hong Kong and will soon join Hunan University as an associate professor. Before that, he received his PhD degree in the Department of Computer Science and Engineering from CUHK in June 2021. His research interests are in deep geometry learning, generative modeling, 3D vision, and computer graphics. And he is particularly interested in 3D reconstruction and generation with high controllability. Most of his publications are presented as top-tier journals and conferences such as SIGGRAPH, TVCG, CVPR, and RCCV. Okay, Ruihui, now the floor is yours.
Okay, thank you. I'm glad here to present my recent works on 3D geometry learning. Today I may talk about the upsampling and the generation. Point cloud analysis. Actually, for 3D geometry, we have different kinds of representation. But here I mainly focus on the point cloud. The point cloud analysis through the deep learning is mostly start from the point net, and also after that, a lot of following works are proposed for different applications such as classification, segmentation, and also detection. Generally, deep neural network often rely on large amount of training data and high quality annotation. Actually, this question is similar no matter for the 2D image and 3D point clouds. However, point cloud produced by the 3D scanning often contain different kinds of artifacts such as the noisy, spirality. Therefore, it's more desirable to enhance the raw data before we can effectively use it for general analysis. Also, the 3D annotation process actually is much more complex than that in 2D images. Thus, the set of the 3D dataset are much smaller and also with limited diversity. So I want to, instead of manually collecting different data, it's more desirable to enlarge the 3D dataset automatically. In my research work, I mainly focus on these two issues. We can enhance the raw data that's specified for the 3D perception. Here, for example, given the sparse input, we can upsample it to get a dense output, and thus facilitating the surface reconstruction. On the other hand, we can also try to learn to generate some gross and new objects to enlarge the original dataset automatically. Next, I will talk about the main idea of these works. First is point cloud upsampling. Point cloud produced by the 3D scanning are often sparse, non-uniform, and noisy. Just look at these examples. Although we have tons of scanned points, but only a few points are allocated to the meaningful objects, such as the pedestrian and the cars. Given such a sparse and noisy input, point cloud upsampling is aimed to generate a dense output, which can provide a more faithful representation of underlying surface. Traditionally, we may use some optimization-based method, but this optimization-based method often rely on some shape attribution, such as smooth surface and accurate normal. Therefore, the performance and the generalization of this method are often limited. In contrast, learning-based method often achieve a better result by only taking the raw point clouds. Here is a general pipeline for the point cloud upsampling. We first get the feature extraction from the input point clouds, and after that, we expand the feature, and after that, we regress the output coordinate. Before we talk about our method, we first elaborate on task formulation, particularly about how to prepare the training data in those learning-based methods. For each model, we crop a lot of small patches and using the Poisson disk to generate a uniform point set as our target output. And when during the training, we conduct a random sampling from the ground truth to get our sparse input to fit into the network. This formulation actually makes the upsampling method often have a good generalization. Here is the visual preview. Given the sparse input, and the previous work also can actually be successful to produce more points. But compared to the previous work, the result of our method is called PU-GAN is more uniform and clean. First, I will talk about the motivation. Given the sparse and the non-uniform input, the previous work just tend to generate more points around the original input, such that the output is non-uniform. But here, I want to emphasize on the uniformity. Look at the two disks on the right hand. Even with the same number of points, but the uniform distribution given provide a better perception and also better for the downstream tasks. In our work, our contributions focus on improving the uniformity of the upsampled result. One of the main contributions is a uniform metric. It's inspired by the mosaic theory, and inspired by that, we formulate a uniform loss, try to give in an explicit regularization. And here is a visual example. Given the same number of points, our uniform metric is sensible to the point distributions. Actually, this uniform metric is also applied for other tasks such as point cloud completion. Another contribution is GAN-based framework design. Actually, we designed the first GAN-based method for the upsampling. Here is the overview of the proposed network. We also provide some design some several modules to enhance the feature learning. But here, if we want to get more detail about the uniform metric and the framework, you please refer our paper. For this work, we also provide a new dataset, and this dataset is rarely used in the upsampling tasks. Here is the visual comparison. We provide the upsampling the result and also the corresponding mesh reconstruction result. As we can see that our PU-GAN can produce more fine-grained detail, such as the elephant nose and the tiger's tails. We also provide a quantitative comparison. Our network actually achieve better performance for all the evaluation metrics. Particularly for the uniformity, our method is also achieved better, indicates that the point generated by our method are much more uniform. Here we also first conduct the upsampling on the real scanned KT dataset. It indicates that our model can generalize directly to the real scanned data without additional training. There is also another research demonstrates that our upsampled result can help for the 3D detection. This framework is also contains some limitation. First, it can hard to train due to the GAN framework, and also it may introduce some extra noise when using a large upsampling rate. Next, I will introduce our recent work, which achieve a better performance and also better efficiency. Here we first revisit the point cloud upsampling task. Essentially, we find it's multiple objective tasks. First, it needs to generate a dense output. Second, you need to ensure a uniform distribution. And sometimes you also need to reduce some noise and also filling some small holes. Existing framework aim to achieve all these goals by designing one upsampling module. However, it's very hard for such a design to meet all requirements at the same time. So a simple idea for our paper is based on its multiple object nature. It can be easier to take a divide and conquer strategy. We first divide the task into two sub-goals. First, this generator produces a coarse but dense point set which can roughly describe the underlying surface, and then we combine with a spatial refiner to refine the coarse point to better cover the underlying surface for distribution uniformity. This framework is quite general. It's a divide and conquer strategy. It's quite simple but efficient. Compared with previous work, our disentangled design has two advantages. First, our framework assigns novel requirements to each subnetworks, and also we allow the two subnetworks to complement with each other, such as is need to a substantial program performance boost. For the architecture design, actually we using for the dense generator, we directly adopt a simplified version from our framework work, and also design a spatial refiner by combining a local refinement and a global refinement to refine the local and the global structure respectively. But when we design the framework, actually after we divide using the divide and conquer strategy. Actually, no matter how you design this from the detail of this framework, the performance is always better. We also conduct the experiments on both synthetic data and the real scan data. Here we first show the comparison result of the upsampling result on the synthetic data. We can see that our point cloud produces more uniform distribution and can preserve the tiny local details. We also show the error map, and the blue means the lower error. We can see that our result when using a larger upsampling rate because our framework is quite efficient. Here we show the upsampling the result on the real scan data, and we also provide the mesh reconstruction result. Our result can produce a smooth surface and also produce the complete surface. Here is another example. Please note that our framework is directly generalized to real scan data. Okay, here I have talked about my works on upsampling. The first work, PU-GAN, mainly focused on improving the uniformity. And the second work, this PU utilized a divide and conquer strategy to improving the efficiency. Next, I will talk about my recent work on shape graphics, shape generation on SIGGRAPH this year. In this work, we present SP-GAN, which is a new unsupervised generative method. We can directly synthesize 3D shapes from a random vector and also promote controllability for part-aware generation and manipulation. And next, those work in 2D images, such as PU-GAN and STAR-GAN, which can already synthesize higher resolution images with fine details. But if you look at the 3D domain, it's totally another story. Although we have achieved some progress in 3D domain, 3D shape generation is still quite challenging due to the large shape variation and high complexity in 3D space. Existing generative model can be roughly divided into autoregressive based, flow based, and GAN based. All of them can synthesize different object from a random latent vector. They often struggle with fine detail, and the generated object tends to be noisy. And it's also hard to find the particle redundance between the input latent vector and the output part. Therefore, the current method does not enable structure-wise controllability. In this work, we design a new generative method, which not only synthesizes 3D object with finer details, but also facilitates structure-aware manipulation. Please notice that our method is unsupervised. That means that we don't need any part annotations. Here we present an overview of our SP-GAN. Basically, it includes a generator and a generator part annotations. And it's quite similar to the previous 3D GAN, but the main difference is the input design. Next, I will talk about why we design like this. Different from a conventional generative method, we design our generator with two decoupled inputs. First, a global pair in the form of 3D sphere, and a local pair which is a random latent code. During the generation, we attach the sample latent code to each sphere point, and the generator learns to transform the input sphere into a physical shape. One important insight in this design is that we simplify the complex 3D shape generation task into a global shape modeling and a local structure adjustment. Actually, we turn the generation task into a transformation or deformation task. We turn the 1D to 3D mapping task into a 3D to 3D task, such that we largely alleviate the learning burden and enable a high quality shape generation. Compared with previous method, our generated object contains finer details and less noise. Another important insight is that our new model can implicitly embed a dense correspondence between the input sphere and the output object. Here we categorize the learned dense correspondence of more shapes, and we can find that the correspondence is consistent across different objects, even with those deformed animals. Here I want to talk about a little bit about the design intuition. I take the generation task as a painting task. The generator can be regarded as a painting brush, and the noise vector can be taken as a pigment. When we do the painting, we always have a canvas. Here I design the sphere as the canvas, which can provide a shared working space. After that, we can build the correspondence automatically. But if you don't add this, you can skip that. It's just an interesting thought when I design these tasks. But such dense correspondence can enable a lot of applications and facilitate structure-wise controllability. Firstly, if we just want to modify the latent vector for some point on the sphere and keep others unchanged, we can just only multiply on the local structure. Let's look at this example. We can only change the chair spec and without touch another area. Further, taking the sphere as a proxy, the dense correspondence can be spread across different objects. Similarly, we can select some part and do the part interpolation between two generated objects. Another application is our learned dense correspondence facilitate a one-shot part co-segmentation. Here, we just need to manually segment one instances and directly apply the point-wise label on the other instances, such as all the other shapes are co-segmented without any extra effort. Here we visualize different objects by our framework. As shown, our generated object exhibit fine detail with less noise and also cover different kinds of local and global structures. Our generated object can be also reconstructed as continuous surface. Our result can also conduct the shape interpolation between different objects. We can see that our SP-GAN enables a smooth transition from the source to the target object. Because we can learn the dense correspondence, but we can just interpolate on the associated part. Here we can keep the inner part and conduct interpolation on the other part. Our model can also perform part composition from multiple objects. Here, given several objects, symmetric parts from different objects, we can pack them together to get a new object. Here is a gallery for different generated objects and also different applications. Because our design is quite simple and effectively, such that we got consistently acceptance from our Asiagraphics reviewers. We also provide an interactive interface. Since our model is rather simple and effective, we can realize the real-time interaction. With our provided interface, its user can select some parts, and we can do the multiplication on the associated part. Okay, in my day I may talk about my works on the upsampling, which can enhance the raw representation, and also the generation, which can directly generate diverse objects. In the future, may also focus on the generation and the reconstruction. As we all know, the 3D representation contains tons of representation. Here we can show the point cloud meshes, so the grid, and also the implicit functions. But here I mainly focus on the generation and the reconstruction, and particularly focus on to provide some intuitive, effective, and flexible controllability. My recent work is focused on the mesh generation and the manipulation. The basic idea is we learn a disentangled representation between the topology and the globe shape, such as we can do the interpolation just on the. Here we can keep the globe shape and just do the interpolation on the topology, and on the right we can keep the global. We can keep the topology but do the interpolation on the globe shape. But in the future, I also like to try to provide more fine-grained contribution with a part-wise relation, and maybe also contain some generation based on the user feedback, and also consider the object functionality. Another interesting paper I saw in archive recently is we can do the text-based generation. Here, just look at the left hand. You can see that the object is quite interesting. Maybe some object does not exist. And we can also, on the right, we can also learn to reconstruct some object from the world image, such that we can bring the 2D image to the 3D domain. Besides, I'm also open-minded to bring geometry learning into the biomolecular modeling. And I saw a very inspired paper from CVPR this year. I'm also interested on this domain. I have some collaboration with some researchers, but I'm just an amateur on this domain. I will explore more. Okay, here I just remind you my talk today. First is upsampling, and the second one is the generation. You can find all the resources on my homepage, and all this works thanks for my amazing collaborators. If for anyone, if you like have any further discussion and communication, you can find me using the WeChat or also on the Twitter. I would like to some communication and collaborating with all you guys. And lastly, thanks for the Asiagraphics committee. I think this is provide a very great opportunity for us. Okay, I think the end. Thanks.
Okay, thank you, Ruihui, for the nice talk. So now we are in the Q&A session. So currently there's yeah, so I have one question about I mean, for all the speakers. So as mentioned by Ruihui, so now I mean, this learning method are developed for this point cloud data, but there are different ways to represent geometry, right? I mean, mesh, volumetric, or even implicit function. So my question is, so is there any difficulty to extend this method to other geometry representation, especially mesh? You know, mesh. Yeah. So.
Yeah, I think I can say a bit. I think for mesh, usually when you try to do mesh CNN or things like that, to try to learn the features from meshes, one issue I found out is we found out is that mesh may be too local. And also the other thing is when you have mesh, the sensitivity to the topology as well as the triangulation is also another issue. Actually, mesh is quite challenging on its own, I think.
Okay.
So that's why another issue that is following up because of this is that if you want to connect the mesh features with other point features together somehow, okay, this is also very difficult. So this is a very good question, I think.
Yeah, but are these challenges are possible to be overcome?
I think some people are working towards this direction.
Okay.
Yes,
I think maybe the graph neural networks may be a good solution to capture the topology in the mesh.
Okay, yeah, that's true. Yeah, because mesh is actually a graph, right? So yeah, that's a natural way to handle mesh.
Yeah, yes.
Also you first.
Sorry. When I designed the SPGAN, actually, if you look at the detail, is some kinds of lack of the pixel to mesh, because pixel mesh also contains a sphere, but it's a mesh. So I designed the mesh is some kinds of inspired by the mesh, but mesh-based framework. So in my mind, I think different kinds of, as we all know, we contains tons of representation in 3D. And each representation has their strengths, and for some cases we can combine them together. Just look at the point detection. I know a lot of work to focus on the voxel and combine the point. They can get a better performance, such that because the voxel is more efficient, the point cloud is more accurate, and combined together you can get a better performance. So it's quite intuitive. The mesh can be more smooth on the surface, but point is easier to handle. So maybe we can combine them together.
Okay, yeah, that makes sense. I mean, so we can use different geometric representation to address a specific problem. Okay, I have another question, which is about this distinctive region detection. So, I mean, this very nice work, and you have also, not just demonstrate the technique. I mean, not just introduce the technique, but also demonstrate in different applications. So one is shape retrieval, and we know shape retrieval is actually a global shape matching, right? So I mean, both shapes are complete. But is this approach possible to be applied for partial shape matching? For example, for strategic object recognition, right? So it's actually a partial shape matching problem. Actually, it's more challenging, right? Because
of course.
Yeah, so is that possible to address this problem?
Actually, in our shape retrieval application, we focus on the intra-class shape retrieval. It means that there is a data pool and it contains the shapes from the same class. So when we do the shape retrieval, we cannot use the previously commonly used the global feature. Instead, we need to extract the features from these local regions, and we use this one as the guidance to extract to retrieve the shapes. So maybe in the future, when we do the part shape retrieval, maybe we can incorporate the part segmentation into existing framework, and maybe we can do a better part-based shape retrieval.
Okay. Yeah. Okay.
Hello, Peng. Yeah, this is Ligang.
Yeah,
so I happened to listen to all of the talks this evening. So very interesting. Hi, Philip. Yeah. So I have a question for you. So
thank you.
In your talk, you mentioned that in the semantic segmentation, you assign labels to edges instead of vertices or triangles.
Actually,
so,
in addition, sorry.
Okay. Yeah. But as far as I'm concerned, that traditional methods assign labels to vertices or triangles, not instead of edges, right? So
no. We maybe let me talk a little bit more detail. So actually, we have a label, an object class label for each point in the scene. Okay, this is one label, and actually we can have another label, which means when we connect two points, two adjacent or nearby point, we can predict whether these 2 points belongs to the same object. Yes or no. So it's a binary prediction. So that's why we have an edge between points and then try to make another prediction. Additionally to the class label, we want to predict whether the 2 points have the same label. Because if we have this kind of edge loss, we can increase the interaction between the features.
Okay, I get it. Okay.
Yeah.
Okay. So
sorry, I didn't make it clear. Sorry.
Yeah, so it's okay. Yeah. Okay, I had another question to Xianzhi, maybe. Okay. So
yeah.
in the work of invariant rotation invariant features, right? So you adopt 2 attributes. One is global and another is local features. Actually, both of them are man-made or handcrafted features. So in the deep learning, so some guys prefer to use end-to-end deep learning network. So is it possible for you to design a pure end-to-end network for this task instead of using global or local features you mentioned?
Yeah, you're right. Our local and global rotation invariant representations are somehow engineered, so handcrafted. So we manually extract these features from point coordinates as network input. Actually, if we design the framework to be end-to-end, it means that we may need to input the point coordinates into the network, and then let the network to learn the rotation invariant representations. Maybe we can do this, but we cannot ensure the purely rotation invariance. So if we design an end-to-end framework, maybe we can address the rotation invariance to a certain extent, but we cannot ensure a purely rotation invariance. So so it is very difficult to design an end-to-end framework, and we directly input the point coordinates into the network and then let the network to be rotation invariance. It may be much more difficult.
Yeah. But think of point coordinates in their work, point net, right? You know, so they learn some local rotation or transformation for each patch or each point. That might be a hint to design some pure end-to-end network. Just my comment. Maybe that might be possible. Okay, so just think about it. Okay. So one comment to the first question, just Peng asked, what's the advantage of meshes over points? So maybe I think different representation are the benefits for different tasks. So I think it's a task dependent problem. I think, yeah, because in some applications, topology, I mean, the connectivity between the points are quite useful. And Xianzhi also mentioned the graph neural network for that. So just a comment. Okay. So overall, good work. Okay, thanks for your talks.
Okay.
Thank you, Li Gang. Thank you.
Thank you, Li Gang, for the comments. Okay, I have one last question, which is about this shape generation and manipulation. So, okay, so now you can learn the data and generate new shapes, right? So my question is, if in case I want to generate shape that satisfy hard constraints, for example, I want to generate shape that are high field, because the high field shape can be, for example, do the CNC mining, that kind of things. So is that possible to, use this learning method to generate that shapes, with some hard constraints?
Yes, actually, I just saw a paper today. I saw a paper extend of SP-GAN to try to compare with a chair. Means that you can make the how to say, their paper is how to make a chair because you can sit on that. This paper is work on this domain. They optimize the human. They can sit on a chair. Yes, do this kind of have maybe physical. They can also contain some physical constraints such as the connection, because different parts may be distract, maybe this not connect. This is kind of physical. Actually, you can I saw some paper works on this domain.
Okay, that's nice. Okay, I think that should be all for this talk. And thanks again, the three speakers for the very inspiring talk. And thanks audience for joining this session. Okay, so thank you again, and I will see you later.
See you.
Thank you.
Thank you.
Thank you. Bye-bye.
Bye.
Bye-bye.